Okay, this is lesson 5.5, the general multiplication rule and tree diagrams. So general multiplication rule is not too bad. Let's look at what they got here. So this is what we studied last week, I guess, before all the snow. Um, okay, so that's the general. So we've got this, we've got to add up the probabilities. If they're not mutually exclusive, then we have to subtract the overlap, right? The intersection of A and B, that's when both events happen. Okay, so here's a question. About 55% of high school students participate in athletic sport. Roughly 6% of these athletes go on to play college NCAA sports. What percent of high school students play a sport in high school and go on to play an NCAA team? So you've got this kind of conditional stuff happening. You've got two events happening here. So what's the chance of both of those events happening? So about 6% or of 55% or roughly 3.3%. Wow, it's pretty small when you think about it. Actually go on to play college sports. So the formula you would use is you're saying that probability of high school sport is 55%. Probability of NCAA team, given that you played the high school sport, is 6%. So what's the problem that the probability that both of those things happen? We're going to multiply those two probabilities together. That's how you got the 3.3% there. So you're multiplying, just a statement, probability of high school and probability of college, given that you played high school. So that's called the general multiplication rule. Definitely write this guy down in your notes. So it's similar to independent events. Independent events we're going to multiply, but the second event is the probability given that the first event has already happened. So it is a little bit different than independent events, but you are multiplying like you do with independent events. And it's somewhat intuitive, I feel like, maybe. For the second event, the first one had to have occurred. Okay. They're just, you don't have to write this down. They're just proving a formula, kind of like we do with algebra. We sometimes prove a formula. And so they're taking the conditional statement we had, conditional probability, and kind of adjusting it a little bit. And that's what this formula is. It's kind of just in a formula that's been adjusted by multiplying by the probability of A, and we get this new formula. But it's quite a bit different. I mean, it's just different than what we do. Okay. Do most teachers have active profiles on social media? Based on a March 2018 report by the American Academy of Child and Adolescent Psychiatry, 90% of teens use social media. Of those, 83% have at least one social media profile. Find the probability. So some people use it without having a profile, right? That a randomly selected teen uses social media and has at least one profile. So we want both those things to happen. Well, that sounds like we're to use the general multiplication rule, right? So the formula was probability of A times probability of B, given that A has happened. So probability of A, what is that? 90%, so 0.9 times, what's the probability given that you use social media that you actually have a profile? So 90% times 83%. We're just going to multiply these two probabilities. In words, that's what we're doing. We're plugging into that formula, probability of A times probability of A given that B has happened. And again, this is somewhat intuitive that you would multiply those two things and you get the answer. So this is, I think we might be getting tree diagrams here. So she hits a snooze button. So there's a 70% chance of her hitting the snooze. If she doesn't hit snooze, then there's a 90% chance she was making the class on time. So it kind of makes sense. She's going to have different probabilities of making the class on time on whether or not she hits snooze or not, because she might sleep in, she might get up on time, those kinds of things. Those are the conditions. So that's actually the hardest thing I feel like about trait diagrams is noticing what the first condition is. The second one is conditional on the first. So I think hitting the snooze and not hitting the snooze is your first branch of this probability tree we're about to draw. Then we draw the second branch from there. Suppose we select a school day at random and record whether Shannon hits the snooze button when she arrives at class on time. That's called a tree diagram. So the way you draw this is you start with, again, the alarm goes off, you do one of two things. So you either hit snooze or you don't hit snooze, right? So those are the two possibilities. That's our first branch. The second branch says if she hits snooze, there's a 70%. So if she in fact hits snooze, there's a 70% chance from that. So you're going to draw a branch from that and put the corresponding proportions there. Notice that on each branch, so there's a 60% chance of hitting the snooze, which means by default, there's a 40% chance of not hitting snooze. If she hit snooze, it said there was a 70% chance of being on time, which by default, those are complementary. There's going to add to 100% or 1. So that's going to be 0.3 that she's going to be late. 10% chance of being late, which means a 90% chance of being on time there. So they gave us some of those numbers, and you have to intuitively use the complement to figure out the rest. We'll do one from scratch in a minute. If you write this down, if you want, just when you have these conditional statements, conditional probabilities, it's much easier for our brain and algebraic, like probability-wise, to organize it with a tree diagram. It's going to really help us. So we can multiply along the branches. So this is what that means. Let's see if they highlight it here. This is nice. Okay, so if you want to say probability of hit snooze and being late, you have to multiply those two probabilities, right? So if you want to say, okay, what's the chance of hitting snooze and being late? You're going to multiply 0.6 times 0.3 to get whatever the answer is, 18% chance, right? So to get the end of the branch, you just multiply. So if you want those two chances, you're going to multiply those two branches to get 42%. We just did that one. It's 18%. If you want to find out not hitting snooze and on time, you multiply those two branches, get 0.36. And finally, the last possibility is not hitting snooze and being late. Those are the chances. And guess what would happen if you add up these four numbers? 42%, 18%, 36%, and 4%. It's going to add up to 100%. So these ends of the branches, even the branches themselves, always add up to 100% there. So that's really nice. And I definitely just do this. When I draw a tree diagram, I go ahead and multiply all those guys out and just get it just to start with. So there's a classic question here. What's the probability that Shannon is late to class on a randomly selected day? So you're just going to add up those two probabilities, the two late ones, right? So 18 plus 4 is 22%. So once you have the tree diagram done with the ends like that done, that's gravy. That's just easy, right? There's what, 22% chance that Shannon will be late to class. Okay. Who likes pop music? Spotify revealed that 47% of its users are aged 13 to 24. 25% are ages 25 through 34, 28% are 35 or older. Suppose that for the 13, so I think with this one, we have, it looks like 3 age divisions. So the first branch is going to be, for our tree diagram, it's going to be the 3 ages, right? You're going to have 3 branches. But then it says, okay, suppose you're 13 to 24, 85% identified pop. So that means 15% did not identify pop. And then for the next age group, 59% identified pop. And for the third age group, 23%. So this just kind of flows. So you're going to start, okay, age groups are first, right? Because the second statements, if you do pop, that was conditional on which age group you're in. And it kind of makes sense, right? Maybe I don't know. I didn't really pay attention to the percentages. I wonder if older people or younger folks would be more likely to listen to pop music. I'm not sure. And we'll find out here. So 85% of younger folks listen to pop music. 59% of the middle-aged, if you call those middle-aged group, listen to pop music. And only 23% of the old folks, the 35 or older, which are, I guess I'm in that group, 23% of those. So it does seem like The younger you are, the more likely you are to listen to pop music. But this tree diagram figures it out. And what you want to do is there's 6 ends of the branches there. You want to multiply all those probabilities to get those 6 branch things. So I'm not sure if that's what they're going to do. So if they multiply that, they just did the one they need. I usually just do them all because I'm going to use them eventually. Usually there's like 2 or 3 questions on each tree diagram. So typically it's not a bad idea to just multiply them all out. They did not multiply the young age group times not pop, the middle age group times not pop, or the older age group times not pop. But those will give you 3 more results. All those results are going to add up to you 100%. But if you just want the probability to be a pop, you add up the 39% plus the 14% plus 6%, and you're going to get the 61%-ish answer there. So 61% of folks overall listen to pop music. And that's a classic tree diagram right there, right? Some conditional probabilities while going in reverse on a tree diagram. I don't know if I see this very often, but let's see. Suppose Shannon is late for class. What is the probability that she hits the snooze button? So she's late for class. So, okay, so this is saying we already answered that question, right? What percent are late to class? Did we get that a minute ago? Late to class was 22%. So 22% is in the denominator here because it's basically saying given, whoops, sorry, get back to it. So given that you're late to class, so that's 22%. That's my denominator. Only out of those folks. What's probably hitting the snooze button that morning? Well, that would be the 18% divided by the 22% here. So the late, our denominator, is the given there. Because again, the given is always our denominator. So that's going to be, we already did that a minute ago. It's 22%. We don't have to add up all those numbers. We did it just a minute ago. And the numerator is the 18%, right? That comes from, if you hit the snooze, it's the 18. So 18, that's what, I don't think you have to write that previous one. I think you just write 18% divided by the given of 22%. The given is that you are late. And that ends up being 81%. Shannon is late 81% of the time, about 0.8 probability that she hits the snooze button in the morning when she's late. So this one's kind of an interesting one, just topic-wise. Many women choose to have mammograms. Unfortunately, the test is not perfect. It gives you false positives, false negatives. It's not perfect. In fact, there's some controversy about the whole mammograms. When should you do it? It changes. It's not always the same. I don't know what they're saying now, but it's not a cut and dry thing because this test is not perfect. And we wish we had something better, I think. Suppose we know that the following information about breast cancer is true. So we're going to kind of take this as face value. So I think these are relatively true-ish. So 1% of women aged 40 or over have breast cancer. That might be surprising. That's a pretty big population there. But evidently that's true. We're going to accept it as true anyway. So that seems like our first branch there because it's not conditional. 41%, which means 99% of women over 40 do not have breast cancer, right? So for women who have breast cancer, so that's conditional. This is the second branch. Probability of a negative mammogram is 3%. For women who don't have breast cancer, that 99% folks, the probability of a positive mammogram is 6%. So first, before we answer the question, let's draw the diagram. So this is what you would do. First, the first branch there, like we said, has breast cancer. The second branch is given that you have breast cancer, what's the chance of having a positive or negative? And same thing for the other one. And you're going to want to find those n values. So multiply all 4 branches there. You can multiply them all out to get those answers. They did this. So to get the probability of breast cancer and so this is basically saying, given that she tests positive. So to test positive, that would be the top branch. So women, so 0.01 times 0.97 would be positive, plus 0.99 times 0.06 would be the positive, right? That's where they get the denominator. Those are all the positive folks, whatever those numbers are. I'd prefer to see the numbers. I guess they're, yeah, that's how you get that one. That's how you get those guys. So the chances are, again, the given denominator and then the top. So given that you tested positive, what's the chance of you actually having it? Oh, wait, this is crazy. I told you this is interesting. So this is saying if these numbers are true, they're probably somewhat true. We usually in stats use real numbers. So if you test positive, so you go to get your mammogram, they say, oh, you have breast cancer. You tested positive. There's only a 14% chance that they're actually right. Wow. That's crazy. So, I mean, that's not great, right? We don't like to see a test that's only accurate. So it's a little deceptive when it says 0.97 because if you test positive, it's only right about 14% of the time. Wow, that's crazy. Okay, you could also organize this information into a two-way table if you wanted to. You could put the numbers there, and that would be another way you could answer the question from that if you needed to. You could draw a Venn diagram of this. All these topics in this chapter kind of go together, but really, I really like the tree diagram for this data. It's really, although this is kind of interesting though, I can see that a lot more folks, it just stands out now, a lot more folks, because I just knew the percentages before, but a lot more folks really don't have breast cancer there. Only 100 out of 10,000 have it in this case. Okay, given that random substance has a positive, the two-way table shows that conditional probability. They're just getting it a different way. Again, probably easiest to get from the tree diagram. Okay, that's your lesson for today. Enjoy the ice, snow stuff.